first one is going to be William Kennedy, who is a managing partner at Arden Labs in Miami. That's where he came from, here to Wrocław. And that's a mobile web and system development company. William is co-author of the book Go in Action, and he is generally working to increase Go adoption through diversity. So let's welcome William Kennedy with his talk about Go.
Okay, now we're good. All right, excellent. Thank you guys for all showing up for this session. I asked quickly before we started who was working in Go. I had a few hands come up. So I'm going to assume that a lot of you have heard about Go, maybe looked a little bit at syntax, tried to play with it, haven't. What's beautiful here is if you've all worked in curly brace languages before, you know this language. I don't even really have to teach syntax. So what we're going to do today is I'm going to kind of give you a high-level deep dive of how the Go scheduler works in the runtime. And then we're going to just start writing some code so you can really see how some of the concurrency primitives built into the language allow you to do this stuff in a very readable way. Now, let's not get anything straight. Writing multi-threaded software is complicated. It is hard. Go did not make that any easier. It did give us some tooling like channels and things like that to allow us to write code that's more readable. But if you all have been writing multi-threaded software, you know how complicated that is. All right, so let's just get started with the scheduler. Now, I'm also going to assume that you already know a lot about how operating system schedulers work, right? In the very, very basics, what's the idea? You're going to have these threads. These are your paths of execution. And that operating system scheduler's job is to make sure every one of those threads gets some time on some core. You've only got 4 cores. Then in the simplest way, then only 4 threads can be executing in parallel at any given time. If we have CPU-bound work and we have more than 4 threads, we're putting load on the operating system, are we not? I mean, context switches are expensive. And so less is more, less is more, less is always more in this environment. So Go's got its own schedulers, part of the runtime that gets built into your program. And Go is not looking to reinvent the wheel. These schedulers are amazing algorithms. They know about hardware. They know about a lot of things. We're not going to rewrite the wheel. So Go is going to sit on top of the operating system scheduler. We're still going to depend on that operating system scheduler to get those threads scheduled on some core and to get our work executed. Because at the end of the day, the platform is the hardware. And if you want any level of performance, well, it's coming from that processor, right? And the hardware itself. So let's do a little diagramming here. I don't like slide decks. I like to try to stay a little dynamic. So let's talk about how the Go scheduler works. Now, as soon as your Go program comes up, what's going to happen here, of course, what's going to happen here is you're going to get a logical processor for every core that is identified on the host machine that you're running on. This is going to model Linux pretty similarly as I'm going to show you this. So we're going to get a logical processor. Let's imagine that we're running on a single core machine and we've got this one P. Now, the next thing that's going to happen is we're going to get an operating system thread. And every one of these Ps is going to be assigned what we call an M. M standing for machine. And this machine or operating system thread is going to be attached to this P, and for every P, we'll have a thread. So I've got 4 Ps, I've got 4 thread. I'm a multi-threaded Go program. Right now, all I am is a single-threaded Go program. Now, there would be a couple of other threads for some other things, but from our perspective, the code that we write in Go, the code you would be writing in Go, would only execute on a particular M associated with a P. Now, there's a couple more things here as it relates to the scheduler. There are Go routines. In Go routines, you can call them co-routines. They have their own stacks. They are independent passive execution, but it's Go, so we call them Go routines. And the Go routine is going to be our path of execution for everything in Go. We'll call those Gs. So at some point, your Go program is going to start up. Main is going to be getting called. We're going to see this stuff. And the runtime is going to create that main Go routine. That main Go routine is going to be assigned to a P executing on some M. And the operating system is going to schedule that M on some core. And we're cranking. All right. Now, there's 2 more things here that we should look at. Every P has what is called a local run queue. I can kind of do it like this. All right. And as we create more Gs, these G's are going to be assigned to a P. Now, there's also another structure here called the global run queue. So let's put up here local run queue. There it is. There's our local run queue. And there's also going to be the global run queue. And the global run queue could be for G's that haven't been assigned to a P yet. There we go. This is really all that we need to know at this point. And again, we like to keep it simple. So a G, just like say a thread at a high level, could be in one of three states. It could be executing on that M. It could be runnable. It's sitting in some sort of run queue, whether it's a local or a global run queue. And it could be waiting. There's lots of reasons why Go routines could wait. We'll talk about that now. So these are our three states. If a Go routine is waiting, it wouldn't show up on this screen. Now, your operating system schedulers are preemptive schedulers, right? They are undeterministic, not real-time OSs we're playing with. When all things are equal, we have no clue which thread is going to be context switched at any given time. Now, this Go scheduler runs within the scope of our application. It doesn't run down there in the kernel. It runs above it. It's running up in user mode, which means that I have to tell you that this scheduler isn't technically preemptive, but a cooperating scheduler. Now, that's like a four-letter word for some people as old as me that had to deal with cooperating schedulers many, many years ago, because cooperating schedulers mean that applications have to cooperate for the resources of that hardware. And I'm going to tell you right now, if I got the hardware, nobody else is getting it. That's just the way it worked. But what's nice here is this cooperating scheduler, the cooperation is happening in the Go runtime. And because of that, this cooperating scheduler actually looks and feels preemptive. When all things are equal, we have no clue which Go routine is going to be scheduled or run at any given time. So a context switch in Go is when the scheduler decides that some G currently running on this particular M is going to be swapped out with another Go routine, preferably here in the local run queue. That will be a context switch, and that's the context switch on the M itself, that M, that thread. Now, there are four basic events that can occur at any given time. They're happening all of the time that can allow the scheduler to make a context switch. The first one is anytime you use the keyword Go, which we will be using today. The keyword Go allows you to create a new Go routine. So there could be potentially a context switch anytime you use Go. Next is garbage collection. Yes, Go has a garbage collector. I'm going to show it off a little bit tomorrow in terms of the things that we do tomorrow. But garbage collection could definitely cause a context switch. Now, any sort of kind of blocking, mutexes, things like that will give the scheduler an opportunity. And finally, what do we got? System calls, syscalls. Syscalls are also an opportunity for the Go scheduler to make these scheduling decisions. All right, so these things are happening all the time in our programs. And that's why it's really going to look and feel preemptive here. All right, so the real model here, the real idea, what we're really trying to do down here in the scheduler is to leverage every thread to its fullest capability. In other words, let's make these threads look and feel like they're CPU bound all day long. Because if they are, there's no reason for them to be context switched, and we will never need more P's than we have cores. And that's really the idea. So imagine something like a system call where this G right now running on this M wants to display something to standard out. What's going to happen? Well, that system call is going to be an asynchronous thing with the kernel, right? It's going to go, hey, I want you to go and make this system call for me, in which case, when that happens, now this G is going to be taken off this P. It's going to be put now in that waiting state. We're going to bring another G in, and that M is just still cranking. From the operating system's point of view, that M never went to sleep. This is the idea. And so we can do all of these independent passive execution. We can do all this coordination. We can do all this orchestration. And from the operating system perspective, we've reduced a large amount of load on it. All right, so at a high level, this is what we're going to picture here. And if we were going to run with multiple cores, we were going to have multiple Ps, multiple Ms. going on there. And then we can run in parallel, not just concurrently. And concurrency is, managing a lot of things at once. The idea is we're going to manage these Go routines to run on that M. And parallelism is about doing a lot of things at once, and we would need multiple M's on multiple cores to make that happen. All right, so this is really when you can visualize what we're going to be doing, this is what's happening here. This is what's happening underneath. Again, the idea is to keep that thread so busy and use less of them that we're going to be able to get more of our work done. All right, so what I really want to do is show off a little bit of how Go has allowed us to write this type of code built into the language. I'm not going to be using libraries and special packages to do this stuff. It's going to be built right in. And one of the things that I like kind of doing in this type of demo is, let's just imagine we were building a very simple search system where we're going to do things, serially. We'll try to make those things run in parallel. We'll see how much time we have after we get some of that code in. And if not, and if we got more time, I'll show you some more cool, complicated, or, more complicated stuff. But for those of you that have never seen Go before, I'm just going to be writing a simple program that will be a binary. Everything in Go has to be in a package. We're not going to get into packaging here, but package main allows us to be able to do that. And then we're going to have our main function. You're all used to having a main function. And just to make sure that my environment is good, we're going to use this fump package, which is going to allow us to display something to the terminal. And I'm already in this folder, so if everything is good here, this is just a big test. Go is the front-end tool, build is the command. Hello, okay, so we're good. Everybody can see that. We got a good size font there. Great. Okay, so here's the idea. Let's, in a really simple way, say that we're going to build a search engine. And so let's just build a type here. We'll declare a type in Go. Maybe we'll call it engine. You can see here that declaring a user-defined type. You're going to be able to read all of this code. Syntax might seem a little different, but at the end of the day, you know this language already. Now, I'm not going to get too crazy here. Let's just give each engine a name. Obviously, there'd be ports and hosts and all that other crazy stuff. We don't need that for this particular demo. We're going to have this name. And let's come back into main for a second, and let's do a couple things. I just know offhand I want to do some randomization here. So one of the things I'm going to want to do is use this rand package. There's a seed function there. And then from seed, I'm going to just take the current time on my machine. And let's see here. Unix is good. That gives me what I need for seeding. All right, so we're just going to seed some stuff here. We'll need that. And next thing I'm just going to do is create a collection of these engines with the different names. So here's our engines. Now, what you're seeing me declare right here is what we call a slice in Go. It's a way of doing a collection. It's a vector at the end of the day. It's a data structure, a 3-word data structure that has an array behind it. All right, so it's just a vector. If you understand vectors, you understand slices. I'm going to be able to initialize this with some engines right away. Now, this is compact construction in Go. I can say engine using those curly brackets, give it a name, engine 1. But this is a little redundant because the language already knows we're dealing with engines. So I'm just going to do this. And let's just, for this demo, say that we've got 5 of these engines that we can hit for different results. So now all I've done is I've just kind of set us up where we're going to have these 5 engines that we can talk to and connect with. Now I want to be able to perform a search on any given engine. So Go is going to let us define some behavior around engines by declaring the methods. So let's just do this as well. We're going to declare a method here. Maybe we'll just call it search. We'll ask for some sort of topic. For now, if we need anything else, we'll do it. And let's just have search display the result itself. We'll make some changes as we go on. One of the things, though, is I want to kind of randomize how long it takes on any given engine to do a search. So let's set up some sort of duration value by using our rand function here in the rand package to generate a random number from, let's do 500 milliseconds. We'll make it faster. Now, Go requires things to be converted to the right types, and I know I'm going to need a duration, so I'm just going to convert that already to a duration value, and time.milliseconds is already a duration. And then I can just use time.sleep. I know we never do this in our production applications, right? No sleeping. And at this point, we're going to sleep, and then we can just say that we're going to print the results that are coming in. So we could just say here that it's going to be whatever engine found some topic or something like this. We can make these changes as we go. And e.name will get us our name, and we already have the topic. Actually, would even be better is to have that duration value in, let's say, %. V is a generic way of doing formatting when we don't want to be too specific. So that's cool. So I got a really simple search engine. We can imagine actually went out and did all that, but we're randomizing how long it took. We're just going to display that we found something from that particular engine in a particular duration. And now just to having our single Go routine, single threaded app here, let's go ahead and just range over these different. Now ranging in Go, all we have is the for. We don't have wilds. We don't have do wilds. The for has a traditional traditional while syntax, traditional for syntaxes. This for range is going to let us range over these engines if I do it right. And E will be a copy of each engine. For now, that's good. We could just do e.search. There it is. Find something about code. Who cares? And we'll range over all of that. And then really, this should be it, right? So we've got our type, we've got our search. We're going to randomize some time. I've got my engines. I'm going to go and run a search across all of these engines. We're really just going to be executing within the scope of main. So if this works, all right, so we could see that we've got this, all these engines found. We can see the longest one took 452 there, 443. And since we're running serially, the amount of time it's going to take is the total amount of time that it takes to do all of that, right? All right, but it would be nice if we could run these searches not, one at a time, but to be able to run them in parallel. I've got an 8-core machine. I got 5 engines here. I should be able to run every search on its own thread, on its own core, and speed that up. In fact, what I forgot to do? I always forget to do this. Let's run this again here using time. Even better. So 836 milliseconds to run that particular search, right? So that's our total. All right, let's make a quick change and run these engines, these searches in parallel. Now, one way I can do that is by creating a Go routine. So I could just say Go search. I could just put the keyword Go in front of the call, but this is going to be a problem because when main dies, this program dies. And all I'm doing here is scheduling those G's to be on a particular P. And if I were to run this code just by saying, let's run these in parallel, please, we're not going to see any output. Because by the time the scheduler can even make a decision, we're like done. Main is gone. So I've got to make sure that main doesn't return until these Go routines are all finished. Now, one thing we can use for that is a wait group. And a wait group is just a synchronous counting semaphore. It comes from the sync package. And we're going to declare that wait group. And I'm going to tell the wait group that we're going to have length number of engines, whatever is in that collection. So now that wait group is going to allow me to keep a record of Go routines that are alive. That wait group has an API, add, done, and wait. So what we're going to be doing very soon is making those done calls inside that Go routine, inside that independent path of execution, so we can decrement that wait group down 5, 4, 3, 2, 1. Boom, we're going to hold main until that hits 0, and now we're going to be playing with at least 5 of the 8 cores that I have here. All right, we're going to make some more changes as well once we go there. What's really nice is we're using the wait group in a very simple way to keep track of these Go routines. But what if these Go routines needed to talk to each other? Before in the past, we'd have to be working around synchronizing access to shared state, right? There's two things you have to do when you're writing multi-threaded software. You're either synchronizing access to shared state, we're using atomic instructions, we're using mutexes, or we have to do some level of orchestration, which in the past we've had to use atomic instructions and mutexes. This is where Go is kind of shining, because when you do have to leverage orchestration, that channel is really going to kick in. Now, channels are really nice because they give us these semantics around signaling and delivery of data around signaling. This is the big thing. It's taken me a long time to learn. When we pull this channel out into the code, I want us to think about signaling. Signaling with data, signaling without data, signaling with guarantees, signaling with no guarantees. Oh yeah, we got to think about all this stuff. Go didn't make it any easier to write this stuff, but it did give us some semantics and better ways to construct and think about these things. And one of the cool things we're going to do with these channels is write a drop pattern once you get to see the basics here. Right, so imagine all of you had to write a DNS server. What are the chances your DNS server is going to be attacked? That's never going to happen, right? No, we don't have to worry about it. Yeah. Remind me not to use your DNS service. Right. It's going to get attacked, right? And so how do you solve or how do you deal with an attack issue like that, let's say on a DNS server? Well, at some point you have to identify what your capacity is, right? At some point there are more requests coming in than you can handle, and at that point you have a responsibility to drop those requests once you're at capacity. I'm going to hopefully show you with enough time how elegant we can implement a drop pattern like that in Go. And again, what I really want you to see as we're doing this is that I'm not using any third-party packages. I'm not even really using the standard library. This is all kind of built into the language, which is allowing you to have code that's much more readable and more easy to reason about. And I think that's why so many people. Now, I will tell you this. I do a lot of teaching, and I see so much over-engineering with these channels. Everybody comes to Go and they go, oh wait, I don't have to use mutex anymore. I don't have to use atomic instructions anymore. This channel's cool. I'm going to use it for everything. Yeah, right? Our number one rule always has to be readability. If you come to my talk tomorrow, it's really going to be a focus around readability and simplicity and not having to worry or guess about performance, because the Go tooling that I'm going to show you tomorrow gives us a very clear idea of what is performing, what isn't performing. I mean, profiling can show you what's happening, but Go has a tracer that can show you what's not happening. And so one of the things that I really want to focus on all the time is let's write code that's readable, and then we can look at the performance later. Right, and I'm going to tell you this. You don't want to know the implementation. It's irrelevant. What you want to focus on is behavior, signaling behavior. That's all that matters, because from a code perspective, you have to be able to read and understand what you're doing there. How it works is irrelevant because they could change the implementation out tomorrow, but your code continues. And this is a really big problem, I think, for a lot of developers. They want to know the nitty-gritty internals. But if you start getting too deep into the internals, you start writing code around those internals, you're really hurting yourself more than you're helping. So I always believe, and I teach when I'm teaching this stuff, you need to know one level below where you're coding. But when it comes to multi-threaded software and concurrency, remember the scheduler that I showed you before? I showed you how that scheduler works. If we were in my class, I would have said to you, please forget everything that I just showed you. Forget it all. Because you have to imagine that every Go routine that's in a runnable state is actually executing. You got 100,000 Go routines in a runnable state, you got 100,000 cores, 100,000 Go routines, and it's executing. Because if you don't believe that there's that level of chaos, you're going to create problems. Data races are nasty, right? You're going to create problems. When it comes to this stuff, you really want to stay away, as far away as possible from implementation, and focus on behavior. In fact, one of the things in one of the classes, what I'll say to you, Go routines are chaos, right? How many people have children in here? Children. All right. How many people have nieces and nephews? Right? Go routines are like children. That's it. They're like children. And in fact, you're not even allowed to create a Go routine unless you're ready to be a parent. Anybody in here ready to be a parent? I'll tell you right now, you want to come into my shop and you say, Bill, I want to start playing with some concurrency. And I'm going to be like, son, you ready to be a dad? No? Get out. Because I'm not teaching you how to write multi-threaded software. I'm teaching you how to keep your children alive. That's what it is. That's why you can't understand internals here. You have to play D. Because I have 5 kids. I've got 5 kids. Now 3 of them in college now. But when they were younger, I mean, imagine one's going to the pool, one's going down the stairs, one's running across the street, and the other one's pulling off their diaper. Which one am I going after? The diaper. I'm telling you right now. That is a long-term mess. All right? But I only get one. And this is why, again, I want you to focus on behavior, not internals and not implementation. Okay, so we're back here with code. Brilliant. Okay, so let's do a couple things here. Go also has anonymous functions, so this is great. We're going to leverage this to be able to call that done, to decrement that count. Now, also notice I'm using closures here. I'm accessing that wait group variable directly from within the scope of this Go routine. Also have a closure bug here because that E is going to be replaced over and over again. Always having fun with that. So let's fix our closure bug. In fact, my linter is probably going to complain there too. Yeah, I get it. All right, so let's just do this then. E star engine. Actually, we're using value semantics, aren't we? So whatever, we'll just pass another copy. Actually, it's really bad to be using value semantics here, isn't it? I mean, there's host and information like that, so maybe we shouldn't be doing that. Maybe we should just pass in I here. Let's do this right, I, and then we can use the right engine for this over I. What's really nice about Go is, and if you saw the talk this morning about value semantics, Go is heavily built around the ideas of value semantics and pointer semantics and when you're choosing one over the other. Because Go is a garbage collected language, we really want to take care about what's on the heap. And Go's garbage collector is about low latency. It won't run for more than 100 milliseconds today, but Go is also about minimizing the use of resources. So it might want to maintain a very small heap that you're throwing a lot of garbage at. It might run a lot, 100 milliseconds maybe at a time or less, but it's still going to add up. I'm not going to pretend that it isn't. But you need the heap. You need to share values across different domains, program boundaries. We just want to be smart about it. So Go has value and pointer semantics in the language, and I'm now using my pointer semantics here to pass in that I to use the right engine. And what we're going to do next here is hold main, which is the whole reason we did all of this work. Okay, so now what I've done is I said, let's run each search concurrently. It's going to run in parallel because I got an 8-core machine. Each one of these Gs will be assigned to their own P on their own M on their own core. And if we build and run this, we should see some faster results. All right. Are you kidding me? Well, if you could have seen that, you would have seen that it happened. Well, that was actually, I got a bug, and you can't see it. Ah! We got some problem there. We're going to have to look at that. Oh, no, actually, I don't have a bug, do I? I'm waiting. Yeah. Well, we'll see what happens as they continue to fix this thing. Okay. What else can I talk to you about that I now can't show you here? We talked about parenthood, didn't we? Oh, yeah.
What would happen if throw an exception?
Exception. You got to deal with that. One of, I think, Go's biggest things is that it puts integrity first. Now, a lot of people complain that Go doesn't have exception handling. I would argue that when you're treating errors as an exception, you're really putting yourself in a whole world of hurt. So Go says, look, we're not going to have exception handling in that traditional where, you're going to worry about your happy path and when you worry about errors later. You're going to worry about errors now. Now, it can be a tedious thing because you're going to call some function, it's going to return an error, you're going to check that error. And, I always kind of bring that to like security. When I got the new iPhone, it immediately wanted me to use two-factor authentication on the phone. It almost forced me, and I was so done with it. I said, fine. And then I spent 20 minutes trying to get it off because it was so inconvenient, right? Like the more secure a system is, the more the pain in the it is to use. And so people kind of equate the error handling in Go as very tedious, but if you don't take integrity seriously, and I think this is where Go is coming from in error handling, then you're going to have problems. And so you're going to have to handle what you want to do in those particular cases. But if you panic and Go, I mean, you've got some serious problems here. You probably want that app to go down. The last thing you want to do is have an app. How many of you have an experience where an app piece of software should have went down and it was held to keep running and now it's corrupting God knows what? We all have stories. You don't have to raise your hand and you're lying because we've all been there, right? So we have to be very, very serious too about when a piece of software can stay running and when it should shut down. Okay, so now you can see here that the total time was what? A half a second. If you look, engine 2 took a half a second. And that's why, because we were at least waiting for that. So it definitely ran in parallel here. There's a few milliseconds in between there and the wait group stuff. There's a mutex underneath that. But you can see now that we're running much faster. We would have been here for a while. Okay. Now, it's probably not realistic for the engine to be displaying its own output here. It would probably be nice if we could get the Go routine to pass, let's say, the results from those Go routines back to the main Go routine. We'll let the main Go routine handle the displaying of these durations. And this is where channel can come in, because now we're going to do some orchestration. We're going to have these 5 Go routines orchestrate with the 6th or the main Go routine with the results that they're going to have. So let's just make a quick change to our search function here. And what we'll do is we'll have it just return that duration value. Why don't we just have it return the duration value? That's what's important to me here. So time.duration. And it's still going to sleep. But what we're going to do then is just return D. That would be kind of cool. So it's just going to return the duration, which means now when I come here and I call this search, we're going to end up with the duration value. But again, I don't want this Go routine to deal with output. It's not its responsibility. I want it to take this duration value, pass it back over to the main Go routine. This is going to be a beautiful situation for channels. Now, what I'm going to do here is use the built-in function make to make a channel that can handle time.duration values. Now, there's 2 types of channels. There's unbuffered channels and there are buffered channels. Unbuffered channels are really special in Go because what they do is allow you to have guarantees that a signal being sent by one Go routine is received by the other. The way that works is the receive happens before the send. So the sender knows that by the time it's done performing the send, the receiver had to happen first. We're good to go. This is really great because guarantees are, I mean, who doesn't want guarantees in life? I got stuff to sell you if you don't care about guarantees. Got a lot of it. And guarantees are important. But there's a cost to the guarantee, and that's latency, unknown latency, because both parties have to come together for that transaction or that signal to complete. In the case of the buffered channel, we're going to be able to reduce latency because the send is going to happen before the receive, but we are going to walk away from some of those guarantees. In this particular case, we can definitely use a buffered channel. So let's do the following here. I'm not going to need this wait group anymore, as we're going to find out. Let me just get this length value from the number of engines. What I'm going to do is add a slot in this channel for every engine that we're going to create, so every engine can perform its send signal with that data without having to wait on us, main Go routine, to receive it. Now, they're all going to probably be coming to that channel to send around the same time. They will have to compete with each other a little bit. There'll be a little latency there, but there won't be any latency on the receive side. So they'll be able to do that. And now what we're going to be able to do here is, instead of calling done, what we'll do is perform the channel send. And that's a send. It's a binary operation where we're going to send that value on the right through the channel on the left. There it is. And then this Go routine is just going to terminate once it's done. Now, we're not going to need the wait group again, so let's do the following. We now have to wait for all of those signals to come in. We know how many there are, right? There's 5 of them here. So we could do the following. We can just use a traditional for loop. So we'll wait for these 5 to come in, and all we're going to have to do here is declare a variable and perform the channel receive. This is going to allow us to receive each duration value now from a corresponding Go routine on the other side. Order doesn't matter. I don't particularly care which Go routine we receive it on. What I care about right now is that we get 5 of them. This is complaining because I've declared a variable and I haven't used it yet. Compiler is very much about, hey, if you're gonna declare these things, let's use them. If not, just get them out of the code. All right, and the last thing we're going to do is display that again. So func.println. Let's see, we had the duration values. Ooh, now you can see here too that I've got I. Ooh, so one thing I just realized I ran into, this is why I love coding dynamically. I don't rehearse any of this stuff. I really don't, because this is the fun stuff, right? I'm about to display this thing, this duration, and I have absolutely no clue what engine has sent this thing. So, you know, just because I'm running, how much time do I have? Where's my time guy? Let's do the following. Instead of just passing, I got 20 minutes left. All right, real quick. Instead of just passing the duration in, why don't we do the following? Why don't we just make this a, just because we don't have enough time here, I want to show you some other stuff, a string, and then what we'll do is we'll do a func.sprintf here, so we could still have that engine name, %s found in %v, and now we do have the engine name, right? Well, I know I'm cheating a little bit here, but hey, if you don't tell anybody, I won't tell anybody. Okay, so we'll send that string over, right? We're going to have our string here, and then we should be able to just display that. That should be kind of cool. And then when that loop ends, we'll know that we received all 5 of these results from the different engines. We are waiting for everything to finish, though. So let's see what this looks like. Here, go build, get that binary, and there we are. Output's the same, right? We're still running at our speed is still based on the slowest engine, but now at least we've separated the concerns. The engine is producing the results. We're able to get those results back, and the other Go routine now is coordinated with those 5, and we're getting that work done. It's kind of like a fan-out pattern, isn't it? Kind of cool. All right, so within the 20 minutes I have left, now that you've got the basics around creating Go routines, wait groups, we've got some channels, let's solve our DNS drop problem. But instead of doing DNS, let's create this scenario right here. You're writing a service, and your service is managing video streams for the entire planet who's watching the World Cup, except for this guy, he's watching Dancing with the Stars. Sorry. And the World Cup is going on, he's watching Dancing with the Stars, and your application is running, and we were told that we have to produce all of this logging because operations needs to know what's happening at any given time. So here's a simulation of our problem, because the logs are going to lock up, every path of execution is going to freeze, and we're not going to know who won the game. And then we're going to bring down the call center for whoever the provider is for that video stream. So look at this piece of code here. What I'm declaring here is a new type. It's called device, and it's implementing an interface or contract in Go called the IO writer interface. It's going to allow this device to be able to stream data. It's taking a vector or a slice of bytes, returns how many bytes it was able to write. And what I'm going to do is have this flag here, and when I hit the flag, I'm going to use Control-C. We're going to cause this device to block up. It's just going to stop. All right? And in main, what we're going to do is create 10 Go routines, and we're going to declare our creative device. We're going to use the standard library logger in Go, log.new, and I'm going to share that device with the logger, so any write that we perform will go through that piece of code I showed you. We're going to launch those 10 Go routines like we did before, and this Go routine, these Go routines are the ones processing video streams, so I'm just doing a lot of writes to the device every 10 milliseconds, and then this is going to allow me to hook into the operating system. So when I hit Control-C, we can cause issues or resolve those issues. So let's run this code real quick so you can see this run. Go build. Here it is. So we're logging, we're watching the video, someone's about to score, and I hit Control C. Every single Go routine in this Go program is now frozen because they can't write their logs. We allowed every Go routine to write to the log at will. Now, obviously, we're going to figure out what the problem is, and it's going to go back. And look at that. There we go. It's running again. But every time that problem occurs, this entire application is down. This is unacceptable, right? In this particular instance, logging is not more important than that video stream. So we have a situation now. We need to be able to detect when we do have blockage on the device. When we do have blockage, we want to make sure that we're not trying to write to it anymore. At the same time, logs are important. So once we identify that that problem's been fixed, we need to be writing logs again. And one of the things we can do here is just write our own logger very quickly and solve this problem. So let's do that right here. Now, normally I'd put it in its own package, but we're running out of time. So let's define a type called logger. And all this type has to do is two things. It's going to be a channel of type string. We're going to have a Go routine whose entire job it is to write to the device. If anything blocks on the device, only this Go routine has to block. This is the only place that we have to deal with detection. I'm also going to be adding a wait group because one of the rules in parenting is you're not allowed to lock your house up at night unless you know every child is safely tucked away in their beds. The Go routine side of that is you have to know when and how a Go routine is going to terminate when you're creating it. I want to know that. There are some exceptions to that rule, but in this case, we want to do that. So the wait group is going to allow us to manage this Go routine that's performing the writes to the device, and the channel is going to be our coordination. Now, the next thing I'm going to need is what I call a factory function. This is going to allow us to create a logger, and we're going to need a couple of things. We're going to need the device that we're going to be using, and we're going to use the IO writer interface. Let's use lowercase letters here for now. Well, who cares? The linter's complaining because there's no comments there. And we're going to need some sort of capacity value to know what the size of the buffer is. The buffer's too small, we're going to have false positive. The buffer's too big, then we're taking more than we should. We'll come up with a number for that. And then we're going to create this logger. So we're going to do some construction here of a logger value. Now, a wait group is usable already in its zero value state. It's already initialized. It's the channel that we have to make. We're going to make this channel of type string, and we're going to set its buffer to that capacity. It's complaining because I don't have a comma there. Okay. Goes very opinionated about code format. All right, so I've got this logger. Now I need that Go routine that's going to actually do the writes. Let's go create this Go routine. What's really cool about the for is we can use a for range to actually receive on a channel. This is exactly what we're going to do here. Again, I'm using closures to access that. So when the channel is in an open state, we'll be able to receive, we'll be looping. And when we close the channel, which is a state change, there's nothing to, you don't have to close channels to clean things up. It's a state change. It will cause this loop to terminate. Now, all we care about at this point is writing to the device. And what's nice is the func package has an fprintf function. And we can use fprintf to write to the device. So it's going to be the device, W, sorry. And V is what we're going to be writing. All right. That's basically it. So as a value comes in off this channel, we're going to grab it. We're going to write it to the device itself. This function works with that IO writer. And once it writes it, it'll come back up and get the next one. So one Go routine, just writing to the device. And if this write blocks, which we're going to cause it, then this Go routine is stuck, but no other Go routines either. But we do have the wait group, right? I didn't finish that. So wait group dot add, it's just going to be 1, and when this finishes, we're going to l.wait group dot done. So now I know here how this Go routine is going to be able to report back that it's terminating, and then all we have to do is return that L and share it back up to the caller. All right, so I've got my factory function now. I can create that logger. I've got the go routine. It knows how to pull off the channel, the orchestration, the signaling with data, and we also know how to be able to set up our termination. Let's do that then, and we'll use a method for this, and we'll call it close, or whatever, stop, whatever you want to call it, shut down. And all we have to do now is two things. We're going to just close that channel, close the channel, L.channel, and that's going to cause this loop to terminate. We want to know when that happens, so now we can say wait group, wait. Not much more to it than that. So when the stop function or method returns, we'll know that that go routine is no longer writing to the device. But the beautiful one here, the thing that we really want to be able to do is mimic this print function here. All right, L print line. So why don't we just do that here? So we'll write another method, and we'll call it print line, and to keep it simple, we'll just have it take a string. And this is the cool part now. We have to be able to detect when that go routine up there on line 21 is frozen, at the same time detect when things are good. And what's really cool here is Go's got a statement called select. And the select has the case. And the case allows us to operate on multiple channel operations, receives or sends at the same time. And so what we're going to do here is we're going to perform a send on this channel, if I do it right, right there. All that's, and one more statement, I'll explain it, the default. And here for now, we'll just say drop. That should be it there. So what this is going to say is the following. Attempt to perform that send on the channel. If there's capacity in the channel, then that send will complete, and we should be able to write that to the device. If the channel fills up, the buffer, because that go routine over there has blocked, eventually we'll run out of buffer space, then that case would block. What the default says is, if that channel operation is going to block, let's not wait here, execute the default case. And just so we can see it, I'm going to just writing drop to the screen. At that point, we know that we're still feeding video. We've lost our metrics and other things, but nobody's going to call the data center on us. All right. So I think we've got an API here that we can leverage. So let's just kind of plug it in now to our code here. So now what we're going to do is call this new. New is going to be our device, and since we're going to have 10 go routines, that should be fine. So that's new is going to now give us our logger. This is already implemented the right way. So technically, this is the only change I should have to make, and we'll make this work. So let's see what happens here now. Let's put a, and it worked, but let's put a carriage return line feed on this, my fault here. And then we'll do it again. All right, so now we're logging. I'm gonna hit Control C to cause that disk issue again. See how quick that was? We're not blocked, we're still feeding video, but we are now in that default case because that buffer filled up. Now I don't know if 10, one for each go routine is the right number. We'd have to do some integration testing or load testing to figure that out. But now we come back and we fix whatever that device issue is, and immediately it starts going again, we get capacity again, and we're going. And we did all of this. We made this one fix here, literally within 40-something lines of code, 40 lines of code, with no library support, really, in terms of the concurrency pieces of this. Everything here is being done with constructs built into the language, the creation of the go routine, the select case at the bottom there. And I really feel like if I asked you this, you guys can read this code. Everyone in here can read this code, understand what it's doing. You may not be able to write this as quickly as I did, but over a small amount of time, you absolutely would. And I think this is why Go is getting so much attention in the systems programming space, because of these types of constructs that are built into the language. Again, Go didn't make writing multi-threaded software any easier. You still have to fight through that and gain your wisdom and knowledge. But it did allow you to write orchestration-based code in a way that's much more readable. All right, thank you guys.